Okay, we got to do the 0.6 is your probability again, but this time we'll be doing compound events using the word and. So if you want to draw a first card black and you want to draw the second card black. Now remember, we've already done that particular problem, but we used combinations. And now we're going to do it a little differently. But before we get started, let me just remind you where we all are. Let's do our recap. So when we recap things, we had talked about the fundamental counting principle, FCP, when an event can happen m ways, and then a second event can happen as n ways. You just multiply those two together and you have the ways that they both would happen. So that's kind of what we're getting at with our and using probability this time, when before we were doing the first event happens, the second event happens, and we were just counting the number of ways the events can happen. So these will be very related. But we also had permutations in the past. We said n items could be rearranged n factorial ways, right? That's a permutation where order mattered. And if you didn't use up all the items when you were ordering them, you had to do an NPR, okay? And we know what those are. And then you decided that if you had these items and you didn't care what the order was, just how many ways could you put some people on a committee, for example, you did an NCR. And order didn't matter. And that was our combinations. And that's what we used to, pick two black cards. And we didn't care what order they were in. I will point out to you that both these permutations and your combinations are doing without replacement, right? If you're inviting friends to your birthday party, you don't invite a friend and then put him back into the bag so that maybe you'll invite him again. Okay, so both of these two have implied no replacement. So let's go on to our probability using and. So we'll use this notation. The probability of the event A happens, and then B happens, okay? So we might just, sometimes we'll just call it and. The implication is it's an ordered thing. A happens first and then B happens, okay? So we have to first ask a question when you have two events. And that would be, does the outcome of A affect the outcome of B? Okay, so what happens first? Does that then influence what happens second? So obviously we have two different types. So if you sort of ask yourself, let's say I flip a coin and then I roll the dice. Okay, so I have these two events. One is tossing a coin, one is rolling a dice. Does the outcome of tossing the coin matter when it comes to rolling the dice? No, it doesn't have an effect at all. So the answer to the question would be no. So if it does not, these are called independent events. And if you say they do affect each other, then of course these are dependent events. And that would be something like your deck of cards, and you draw one card, you look at what you have, you do not put it back in the deck, and you draw the second card. So obviously you cannot draw that first card again because you didn't put it back. So the odds change. So let's continue talking about these independent events, okay? This was the, for example, tossing a coin and then rolling a dice. So what we do is we use a rule for this. If you have the probability of event A, and the question is and B, okay, and this implies an order, then it's the probability that A happens times the probability that B happens, okay? But because they're independent, the order doesn't really matter. Okay, so all you have to do is multiply these two probabilities together, much like the fundamental counting principle allowed us to multiply the number of ways together. So let's do this probability of tossing a coin and getting a tails, and then rolling the dice and getting a 3. Okay, so the events are toss a coin, roll a die. So I want to know, if I did that, what's the probability that I get a tail and a 3? So that's simply the probability of getting a tail times the probability of getting a 3. And obviously the probability of getting a tail is 1 and 2 times the probability of getting a 3. Remember, that's one successful outcome from the dice. There's a 3 on only one side out of the 6 possible outcomes. So 1 in 6. And obviously we're going to get a 1 in 12 as my answer for that probability of getting both the tail and the 3. Now, I don't want you to just take my word for it. It kind of makes sense. We all like this. What's really good, too, is because each probability is less than 1, when you multiply two numbers less than 1, you never get anything more than 1. So that's a good thing, because we don't want that. But I also want to check this result, just to really convince yourself that what we did was right. And we're going to do it using a sample space. So if I were to write out the sample space from tossing a coin and rolling a die, what would that space look like? It would look like tails with the 1, and then maybe tails with the 2, tails with the 3, tails with the 4, tail with the 5, and a tail with a 6. Those are all possible outcomes. Okay, so I'm doing a sample space where you list all the possible outcomes of tossing a coin and rolling a dice and recording the result of each. The other possible outcomes are heads with 1, heads with 2, heads with 3, heads with 4, heads with 5, and heads with 6. So that's my complete sample space. Now when I go to calculate the probability of tails and 3, how many successful outcomes are there? There's this one successful outcome out of the total number of possible outcomes. And if you count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, there are 12 possible outcomes, so that would be your probability. And indeed, that's exactly what we got before. Okay, so let's look at those events that are dependent. Okay, the outcome of the first one will definitely affect the outcome of the second one. So in this case, we want to have the probability of A and B is equal to the probability of A that the first event happens times probability of B. So far it's looking very similar to independent, but this time the probability of B has to be calculated with the understanding that A happened first. So that's what we call a conditional probability. Okay, this right here is a conditional probability. And you read that. Let me write that out for you. Okay, so that P, the probability of B, given that, this little vertical line symbol is a given symbol. So it's the probability of B given A, which means it's the probability that B happens given that A has already occurred. So it's a conditional probability. It depends on A. So this is the example of dealing two cards from a deck without replacement. Okay? So let's be clear. One example would be draw two cards. Hold on. Let's see, where was I? Draw two cards without replacement. So once you draw a card out, it stays out. So in this case, we want to imagine what is the probability of getting 2 aces. So the implication there is your first card is an ace, and the second card is an ace as well. So that's going to be the probability that the first card is an ace times the probability that the second one is an ace, given that the first was already an ace. Okay? So how do we calculate this? The probability that you get an ace on your first card is just the number of aces in the deck, 4, over the number of cards that you had to choose from, 52. That one's easy. But then we go to this one, times, because it's an and, so we use that multiplication. The probability that the second card is an ace is the number of ways to get how many aces are left in the deck. How many ways are there to get that second ace? There's only 3 aces left. Out of the number of cards that you had to choose from, remember one was already picked out of there, so there's only 51 cards left in the deck. And so we have the probability of an ace times an ace, which we could calculate. Get your calculators out. I'm going to start reducing it because that's what I do. 3 and 17 is 1 and 17. 3 and 51, sorry. It's 1 and 17. 4 can come out of that, and a 4 can come out of that, 13. So we end up with 1 over 13 times 17. Let me work that out quick. I'm not that good. 221. We're going to get that number a lot, actually. I should remember that. But that's your probability of getting 2 aces. Let me do one more thing. We came up with an answer of the probability of 2 aces was 1 out of 221. And we did that using conditional probabilities, the 4 out of 52 and then the 3 out of 51. But remember, we did the same sort of thing the other day. I think we might have used kings or 2 black cards or whatever we did. There's that other way to do it. So let me compare these 2 ways for you so you don't get confused between the 2. They're really identical ways. If I were to use combinations to find the probability of 2 aces, then I would have said, how many ways are there to choose 2 aces from the 4 possible aces, divided by the total number of ways to choose 2 cards from the 52 cards available. And if you work that out, you find out that those are indeed the exact same thing. Okay, so let's do another example. Remember, we have to pay very, very close attention to how questions are worded, because almost every word is very important and can change the meaning of the question. So I'm going to ask another question. I'm going to ask, what is the probability given? I have to always start with the given that you draw 2 cards from a deck of 52. What is the probability that you get an ace and then a king? Sometimes they might even say, what's the probability that you get an ace on your first card and a king on your second card? Okay? So I've very much told you who is first and who is second. I've very much told you that the order does matter. Okay? So in this case, you're not going to do combinations. Okay? No combinations allowed here because the order matters. Now, why was it okay before? Well, before I had 2 aces. Did I care about the order up here when I was looking at 2 aces? It's an ace and then an ace, but the order doesn't matter because they're both ace and ace. It didn't really matter which one was first. So the order didn't matter there. I could go ahead and do combinations, or I can use my conditional probability. But here I have an ace and then a king where I want the order to matter, so I'm not allowed to use this alternate method. I have to use the conditional probability. But otherwise, it's going to be very much the same. Okay? Watch what happens here. It's going to be, according to my formula, I take the probability of the ace times the probability of the king, given that vertical line, given that the ace was already drawn. So let's calculate this probability of getting an ace on the first card. That's 4 aces out of the 52 cards available. Again, this was no replacement, times the probability of getting a king. Well, there are 4 kings in the deck I could get out of the 51 cards that are available. Okay, so this is going to be a very different kind of question than the 2-ace question. You see how it's different. 4 out of 52 times 4 out of 51. And you get the 4 over 663. All right, having said that, I'm going to backtrack a little bit. I didn't want you to use combinations because I wanted to make this point that order does matter. But there actually was a way to use combinations if you really like combinations, so let me show you how you could do it using combinations. So using combinations, and I think we did this the other day, so let me get this down for you. It's going to be, how many ways are there to choose how many ways to choose the one ace out of the 4 aces available times the number of ways to choose the one king times the 4 available divided by the number of ways to choose 2 cards from the 52 cards available, which is just 4 times 4 over this 52 times 51. Okay? So there actually is a way to do that using combinations if you like those. Okay, we're still talking about drawing 2 cards, okay? But this time, I'm not going to order. I'm not going to tell you who is first and who is second. But we are talking about 2 different kinds of cards, okay? So we're going to draw 2 cards, and the question is, in any order. Okay, so I have not put them in an order. Another way to do it is just to say you have 2 cards in your hand, okay? So this is 2 cards in your hand. You don't know which one got there first. 2 cards in your hand. So you don't know which one got there first. So we're going to do some of these probabilities, and we'll be using different cards so that you can tell them apart. Okay? So for example, if I had the probability of getting an ace, king, hand, okay? Well, I want to say to myself, I'm going to show you these 2 ways. That's the same thing as is the probability of getting ace, then king, or getting the king and then ace. The order didn't matter. So both of those are legitimate ways to have an ace-king hand. So as long as I can use the or, then this is equal to the probability of ace, then king, plus the probability of king, then ace. Okay? So hopefully you see the little bit of a distinction that we're doing here. So I'm going to go ahead and calculate the probability of ace, then king. That's exactly what we did before. It's the probability of the ace, 4 out of 52, times the king, 4 out of 51. There's your conditional probability, right? You did not replace the card. So that's the ace, then king. And I'm going to do the same thing. I'm going to calculate the probability for king, then ace. So how many kings are there? 4 out of the 52 cards available. So you see how the probability of king changes? Before, the probability of king was 4 and 51. Now the probability of king is 4 and 52. So that's your conditional probability at work. Probability of king on the first card, 4 and 52, times probability of the ace on the second card, 4 and 51. Well, you know, you probably guessed this was going to happen. Those are identical probabilities. Okay, they're the same thing mathematically. So you work it out. You know, you could just call this 2 times 4 out of 52 times 4 out of 51, because I have 2 of them that I'm adding together. So I want to show you another way to do this, so we don't have to keep doing this. It's ace then king, or it's king then ace, and you know, sometimes there's going to be a lot of different ways that it could happen, that we could rearrange that hand. It could have come in any arrangement. So let's imagine the probability, next, maybe erase that, the probability of an ace-king hand is equal to the probability of an ace then a king times the number of ways you have to rearrange, because they're all good ways to rearrange ace-k. Now we can do this because they all have the same probability. So we just have to figure out how many ways that was. So let's do this way. Again, here we are calculating the probability of an ace then a king. So it's the 4 over 52 times the 4 over 51. Now, how many ways are there to rearrange 2 items? I have 2 items to rearrange. So remember, the rearranging is the 2 factorial. If there were n items, I would have n factorial ways to rearrange. And that's my answer. And of course, 2 factorial is the same as just a plain old 2. So these do indeed agree. So to continue our conversation about dependent events and dependent probabilities, I want to go back to the formula that we had that said if you do the probability of A and B, okay, and this implies an order. If I don't say anything else in the, in the directions, like 2 cards are dealt, what are the probabilities that you get these 2 cards? If you get 2 cards, and it's like, imagine getting 2 cards, you pick them up together, you don't know which one comes first. But if I just write A and B, I am implying that A happens first and B happens second. So anyways, we had this rule for A and B. You could do the probability of A times the probability of B, given that A has already happened. Okay, so there's the formula we're going to be working with. So remember that one. When it's when the word is and, the operation is multiplication. And here we have a conditional probability. So I'm going to give you a problem that says, fun stuff, 25% of your survey responders, this one. Sorry, 25% of your customers order chili. So they come in and they order the chili. You also notice that 4% of your customers order chili and a baked potato. Okay? I'll just call it a baked. So the question is, how many, or what percent, what's the probability? What's the probability that somebody's going to come in? What's the probability that someone orders a baked potato given they ordered that chili? Chili. Okay, so we're going to do this. Question. So the first thing you want to do when you do this is you want to figure out what is the order that we're talking about. So for this, what happens first is ordering the chili. Okay, it's the one that you have, this unconditional probability about. plain old ordering chili, that's going to be first, okay? So ordering chili is P of, let's say ordering chili is like A, the first event. And then ordering a baked potato is a second event, okay? So if I wanted to calculate the probability of ordering chili and ordering a baked, let's just work out the formula with it in this order. That's going to be the probability of ordering chili times the probability of ordering a baked, given that ordering chili has already happened. Okay? So now that we have that worked out, we can use our numbers and start solving things. So what is the probability that someone comes in and orders chili and a baked potato? 4% order chili and baked potato. So that's a 4 in 100 chance. Okay? That's going to equal the probability that you order chili, which is your 25 over 100, times this probability of baked given chili, which is X. And indeed, that's what this is asking for. Remember, let's go down here. What's the probability that someone orders baked? So that's probability of baked, given that they ordered chili. Okay? So that's what they're really asking for. So I have to work out the math now. Let me do it down here. I'm running out of room. 4 out of 100 is equal to 25 over 100 times this, what we're interested in. So let me multiply both sides by 100 over 25 to solve for X, right? Because that's going to make X be all by itself, because all those things will cancel. So I have plain old X equals, and on this side I have 4 over 25. So 4 over 25 is the probability that somebody will order the baked potato given that they've already ordered the chili. And that's 16% if you look at 4 over 25. Okay, another good way to deal with conditional probabilities is by using a two-way frequency table. So this sort of organizes your data in a nice way that makes it pretty easy to work things out. And I will note that this is a very popular kind of item on a SAT, particularly the new SAT style questions. So let's make sure we do this pretty well. I'm going to put up a data chart. Okay, so what we've done here is organized our data. You have a group of students who can be divided into juniors and seniors, okay? And you also have that same group of students who could have been divided into varsity and JV, okay? So, you know, you've got all the different combinations. If you are a junior and you're in a varsity team, there's 36 of you, you know? And then I could ask you, how many are seniors and also JV? And there's 257 of those. I could ask you, how many juniors are there? The answer is 312. How many varsity athletes are there? And the answer is 87. So we're doing okay. How many total students are there? And you should say 720. So if we understand this data chart, I have a question for you. Okay, so the question is finding the probability that a student chosen at random from any of the students represented by the chart, find the probability that a student is a varsity given that he is a junior. Okay? So, what comes first? He's a junior comes first. So the probability of junior and varsity, okay, is equal to the probability of being a junior times the probability of being varsity given that you're a junior. Okay? So there's that formula we've been using of two dependent events. So, what is the probability of being junior and varsity? Well, junior and varsity would be this number right here, 36, out of the total number of students, 720, is equal to the probability of being a junior. How many juniors were in here? 312, over the total number of students, 720, times this probability of being varsity, given that he is a junior. Well, that's just what I'm asked about, so let me call it x. Okay? That's what we're asked to find. So when I go ahead and I start calculating this, the 720s are going to cancel. I end up with 36 over 312 is equal to x. You can work that out, 12 over 104, blah, 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 and you get something approximately 11.5%. All right, I have another question for you. I'm going to let you do it as a you try and see if you can get the right answer. Let me put it up here. Okay, so I've actually given two questions for you here. This first one and then this second one down below here, okay? So, and they are two very different questions, and I just want you to see the contrast between the two. Number one, find the probability that a student is JV given that he is a senior, okay? Number two, find the probability a student is a senior given that he is JV. So you always have to ask yourself what comes first, and it's always the thing that follows the given that. That's always going to be your first event, okay? So try and work those out and see if you get the right answer, and they will be two different answers. Pause it because I'm about to put the answer up. Okay, so hopefully you were able to spend a minute and look at that data. The first one, 83%, and the second one, 48%. You're both looking at the students who are both JVs and seniors, but in one case, you've got only 308 students that you're considering, and in the second one, you're considering 533 of them. So the probability is actually much different because of the initial condition. All right, so I just want to do some more examples of problems. We've covered everything, but I just want to show you some of these problems that get more complicated because it's a combination of using ors and ands in the same question and the same solution. So the first one we're going to look at is, imagine you're being dealt 5 cards. You don't care what order they came to you in, so 5 cards are dealt. I'm going to say it this way. 5 cards are dealt. What is the probability that you get exactly 2 sevens? Okay? So I'm not going to worry about what order you got them in. 5 cards were dealt, you picked them up, and you looked in your hand and you said, oh, look at these 5 cards that are in my hand. So when you see the word exactly, that means you have 2 sevens, but you don't have 3 sevens or 4 sevens or 5 sevens. So the first thing you have to do when you see the word exactly is you have to say, well, that means it's the probability of exactly 2 are sevens and 3, so there's an and, 3 are not sevens. Okay? It's supposed to be an S. So here's your and, okay? But it's actually even more than that because it's the, one card is 7, and a second card is 7, and a third card is not 7, right? So you really have all those ands together, okay? What makes this one hard, though, is we don't care about the order, okay? So what we're going to do is we can solve this problem 2 ways. We could do, how many ways are there to choose the 2 sevens from the 4 possible sevens? not caring about the order, so it's a combination, not a permutation, times the number of ways you can choose the 3 non-7s. And if you think about it, there are 48 cards that are not 7s, okay? Out of the number of ways you could have chosen the 5 cards out of the 52 cards available. So this is also a fundamental counting principle working for you and all of that. So here's a good one, and I don't actually have the right answer. Let me take a minute and get that for you in a minute. But I want to talk about the alternate way of doing this question. Here we are using combinations, but we could also use conditional probability if we remember that because the order that I get my 7s and not 7s doesn't matter, I have to remember to rearrange them. So let's imagine getting the probability of first a 7 and then a 7, right? And then a not 7, and then a not 7, and then a not 7, right? So we can imagine it in this particular order, but then since all the orders are good, I'm going to times the number of ways I could rearrange them. All right, so let's calculate this conditional probability. The probability of getting the first 7 is 4 out of 52, times the second 7, 3 out of 51, times something that's not a 7. Well, there are 48 cards that don't have a 7 on them, but there were only 50 cards to choose from. So then there were 47 with 49 to choose from, and then there were 46 with 48 to choose from, times the number of ways to rearrange 5 cards is 5 factorial, but don't forget we have to divide that by the indistinguishables, okay? Some of these are indistinguishable, so when you start rearranging them, you can't tell it apart. That doesn't count as a new arrangement. So there were 2 7s that were indistinguishable, and there are the 3 7s that are indistinguishable. So that comes out to be the answer for that, okay? And those should be the same number. Okay, here's one more example to give you what I'd promised before, a combination that uses both and or. And that's the idea of you're going to pick 4 marbles from a bag that contains 7 red and 8 blue. But the problem says, find the probability that you have chosen at least 3 blue. And we talked about that word at least 3 blue once before, the word at least, and you just want to break it down. What does the word at least mean? And in our case, since we're picking 4, that is the probability of 3 blues or 4 blues. That's the only way to make at least 3. And we're going to remember that since I'm already doing 4 blues here, then this has to be 3 blues exactly and not 4 blues. So let's make sure that other one is red. Okay? So here you see where I have the or word, and that's going to turn into a plus sign. So this is the probability of 3 blues, 1 red, plus the probability of 4 blues. And I say it's a combination because here you're going to say 3 blues and 1 red is the probability of getting the first one blue, the second one blue, and the third one blue, and the fourth one red, right? Times all the ways that could happen, because I really don't care about the order, okay? And the same when you're calculating the probability of 4 blues. You need to say first one blue, and the second one blue, and the third one blue, and the fourth one blue, and so you multiply those together, okay? So there's both addition and multiplication going on in the same problem. And I also want to point out, I don't really care about the order, right? I'm just trying to grab 4 marbles out of the bag. But do I need to rearrange my 4 blues? I certainly will have to rearrange my 3 blues in a red, right? Because I could have done the red one first. But when you have 4 blues, they're all the same. You don't rearrange them because every arrangement looks the same. Okay. If you insisted on arranging them, you would say 4 items, 4 factorial, divided by the number of indistinguishables, 4 factorial, and you just get 1. So don't worry about rearranging when all the items are identical. They're all blue. So let's just go ahead and work this out. The 3 blues. Let's see. The first blue, 15 is my total. Hold on one sec.
Actually.
All right, sorry, I got to pick up again. First blue, second blue, third blue, a red, there are 7 of those, times the number of ways I can rearrange the 4 items when 3 of them were indistinguishable, plus, okay, all these were times because they were and, but this is a plus, the 4 blues, so let's see, blues, there were 8 of them, so 8, 15, 7, 14, 6, 13, 5, 12, and no need to rearrange those, and you should be able to get that answer.